Okay, this is a conservation of energy problem that involves a block and a spring, and also involves friction. So we have a non-conservative dissipative force and the work that that force does in relation to total energy. And also, this is a problem that is going to involve optimization. So we're actually going to take a neat step beyond energy and use the velocity function that we get to find its maximum. Okay, but let's read the problem. So in this problem, we have a um, package handling system with a given mass of 1.6 kilograms, and it's attached to a spring. The spring constant is given, as well as the initial compression. So that's the initial state of the system. And then the block is released, the spring uncompresses, and we're told that the surface on which the block rests has a friction coefficient. So it's a level surface, but the friction coefficient is given as 0.3. And then we are asked, when the box has traveled 0.28 meters, which is the point where the spring has reached its rest length, then the box loses contact with the spring. So the question there is, what is the speed of the box at the instant it leaves the spring? Okay? Because basically the idea is that the box isn't attached to the spring, so as soon as the spring starts decelerating, because the spring itself, when it reaches equilibrium, would start to decelerate because of that force acting on the spring, and we are ignoring the mass of the spring. But the box still would have inertia, so it would not accelerate at the same rate as the spring, so it would then move forward at a greater rate, even though of course it is slowing down from friction. Okay, but it was slowing down friction the whole time as it was moving out to the equilibrium length. So let's go ahead and put in a picture here. Okay, so here we see a setup just showing the initial compression and the two energy states, so E1 and E2. So when the system starts at E1, the box is at rest and the spring is compressed. Okay, by the time that we're interested in solving for the velocity, that's 0.2. So the energy at 0.2, E2. Well, at this point, the box is in motion, the spring is at rest length, and the friction has removed some mechanical energy from the system. Okay, so this is the what we should be considering when we're writing out our equation, our conservation energy equation. Okay, and our method of solution is going to be conservation of energy. Okay, so our method of solution just comes down to one equation for part A, and that one equation is simply E1 equals E2. Okay, and we just have to expand on that and actually write what E1 and E2 are. All right, so let's start that step here. So E1 is going to be 1/2 K D, as shown in the figure, squared. That's going to equal the energy at E2, which has a kinetic energy component, so 1/2 mv2 squared, and then it has a work of friction component. Okay, so why does it make sense to put the work of friction on the E2 side? Is because there was energy to get to that point, right? There was energy that work took. So if you want to put the work as a positive term, right? This is plus, and the work here is actually going to be positive. Then you want to put it on that side, the side where it's removed. Okay. And we have to write it as a positive, okay? So we're already taking into account the cosine of 180 degrees between the friction force direction, as a vector, and the direction of the displacement vector. They are anti-parallel, so the work of friction is negative, but we have already moved it over to the other side. Okay. All right, so let's plug in our, or expand things, let's plug in a little bit more. All right, so our left-hand side is still going to be 1/2 kd squared. And we'll have our 1/2 mv, okay, 2 squared. And then the work of friction is going to be the friction coefficient times gravity, okay? And so this whole expression here is just the friction force. And we know that it's simply mu k Fn, or mu k mg, because the surface is flat. So the normal force is exactly equal to the gravitational force rather than a component of it. Okay. And so then we just want to solve for V. Okay, so if we go ahead and solve for V2, we're going to obviously get something inside the square root. And you can see we're going to have a K D squared over M term. And then we'll have a 2 mu K G d as our second term. And the reason there's no m in the second term here is because we've divided out m from everything, as well as multiplying each term by 2, right, in order to get rid of the 1/2 before we square rooted. And, of course, that caused the m to cancel out of the term with the friction coefficient. Okay, so let's plug in our values over here. Okay, so we want to take the square root, and that's going to be k, which is given as 45. And we're going to be multiplying that by d squared, which is 0.28 squared. Okay. And that's all going to be divided by the mass of the block, right, the inertia of the system, which is 1.6. Okay, and we got our second term here. And that's just going to be 2 times the friction coefficient of 0.3. And then that's going to be multiplied by 9.8. Okay, and then we've got our distance, which is given as 0.28, right? Because that's the distance of the initial kinetic energy, and now it's the distance that's been traveled. Okay, and then I got to insert a forgotten multiplication symbol here. Okay, all right, so, that looks good. Let's see our number here. Everything checks out. Okay, so we have a velocity when the block loses contact with the spring at the spring's equilibrium point, and that velocity is 0.747 meters per second. Okay, so that's what we were asked for in part A. In part B, we're asked, well, you know, where's the maximum velocity take place? Now, it's really tempting to say that the maximum velocity is going to take place at the equilibrium, because if it wasn't for friction, then at the equilibrium point of the spring, all of the potential energy of the spring, right, that energy that was in the E1 location, would have been converted to kinetic energy, and you'd have, that would be the peak of kinetic energy, because all the energy that's in the system is now the energy of motion. However, some of that energy has been lost, and it's being lost at a steady rate due to the work of friction, and that means that somewhere between the velocity of 0 when the spring is released and the point where it's traveling at and leaves the spring, it's actually faster than at the equilibrium. Okay, so it's not going to occur at the equilibrium. And let's see where it is, right? You know, and it's hard to have some intuition for this. It's hard to say, oh, is it going to occur at 0.22? You know, because it's almost all the way to equilibrium. Does it have to happen sooner in the process? You know, and it all depends, obviously, on the relative strength of the friction coefficient to the spring constant. That's what we're going to see, and that's really what we should expect in our result as we simplify everything, that we should absolutely see a dependence on those. Okay, so let's run through the math. All right, so hopefully the concept makes sense. So to find V max, we are going to take the derivative of V with respect to position, to x, okay? And so that's going to be dv dx, okay? Now, obviously, I've defined my initial displacement as d, but we'll define the actual coordinate as x, okay? And so that way we don't have any ambiguity there. And importantly, for making our lives easier here, the dv squared dx will have a 0 at the same place as dv dx, okay? And the reason for that is all we're saying is that the location of velocity squared, you know, the x location of that point where velocity squared is maximum must be the same x location as where x is squared, or as the same x location as where v itself is squared, rather than where v itself is maximum, rather than v squared being maximum. So let me write that out. So I can say, since v squared will be max at the same location as v. Okay, and you might say, well, can we really do this? Does this work out mathematically that the derivative of a function squared has an extrema at the same location as, or rather a 0, which represents an extrema from the original function, as the derivative of just the function not squared? How is that? Are we sure of that? Well, think about it physically, because what we're saying is that the location of maximum velocity squared, it has to be the same location as velocity, maximum, because you have some certain value, 5 meters per second. That's your maximum, right? That only reaches 5 meters per second at some location. Well, 5 squared is 25. That's bigger than any other squared number, any other squared velocity. So, if the math said it wasn't true, then then the math would be wrong, right? Because physically, it absolutely has to make sense. All right. But anyway, that explanation aside, we can go and take a look at just the math and then working it out, right? It's pretty easy derivative now that we don't have to take the derivative of the original function, right? So we don't have to worry about the chain rule, right? We can just make our lives easier. Okay. So the derivative of the velocity squared function with respect to x is just going to be negative kx over m, okay, plus 2 mu kg, okay? And set d squared with respect to x equal to 0 to find location of v max. Okay. All right. So let's just get that last line in. All right. Okay. All right. So let's just want to make this visible. So the final calculation is going to give us that x, okay, at v max is just going to be x max equals, right, just solving from this equation here, all right, just solving this equal to 0, all right, is then just going to give us d, okay, is going to give us a mu k mg over k, okay? And so, basically what we did was we just, moved this 2 mu k g term over to the other side, cancel out 2's from both terms, right? And then that also cancel out the negative, because of course we wouldn't expect a negative x, because we are assuming that x starts, right, our coordinate system here, and not just assuming, but we set and solved in a way that x equals 0 was right here, right? And then positive x was of course towards equilibrium. But then we just had our m term that we multiplied, and then we divided by our k term here, okay? So we get our expression. Now, does it make sense? Well, let's see. I mean, basically, we're saying that the x location is larger when the friction coefficient is larger, and it's going to be smaller when the k value is smaller. Okay. So let's just pause and make sure this makes sense. Okay. So just now, as I was reading out the result, I realized that I had my coordinate system incorrect. I wrote that down wrong, so I want to make that correction. Because we'll take a quick look at why that is. So this was our original velocity, right? And what we did is we then called x a variable, where d was our constant, right? That was our initial compression, all right? Well, let's think about it then. Really, we just changed d to x. Well, d actually is positive in this direction, right? So d actually grows with compression because we had a positive value of 0.28. We didn't call that negative d. We could have, right? We could have defined a coordinate system that was negative towards the left. Many coordinate systems are, but we didn't. Okay, so that's the positive x direction. And then likewise, we have I mistakenly called x equals 0 the initial point of the front of the box. That's also not true. X equals 0 is equilibrium, just as d equals 0 is at equilibrium. Again, because all we did is just redefine d as x. And so then the reason I was able to catch that mistake in my my addition to the figure above was that when we're looking at this result, it doesn't make sense. unless, and this result right here, it doesn't make sense unless we consider that x equals 0 is at equilibrium. For a number of reasons. One I'll point out here is that if we're looking at the derivative of velocity with respect to x, well, we know that that x isn't changing at equilibrium. Okay, or at least not at equilibrium. There's no longer a force. Therefore, the velocity can't is momentarily at rest, right, for a spring without friction. So we always have no acceleration at the equilibrium at that point in time, right? So the derivative of velocity with respect to time, but also we're not going to have velocity change with respect to position at the equilibrium, because at that moment in time and that moment in position, the velocity is constant, right? So in other words, this, and that's when we plug in x equals 0, this term here should be 0, because there should be no change in velocity as a result of the springiness, as a result of the spring, k, and so on. So then we see, and sure enough, that the only change in velocity with respect to position is mu kg, because friction is still acting. So that's a good check of the coordinate system. But again, we could have just, I should have just carried over and just kept all the rules for d. Obviously, should apply to x as well. Okay. So then, real quick, making sense of the result, as mu k gets bigger, x gets bigger. Okay, so and x is the distance from equilibrium. So in other words, the peak velocity would occur, maybe here or here for a very large mu, and for a very small mu, especially a mu of 0, the velocity position x max is going to occur as close to equilibrium. And in fact, if we plug in friction, if we make this system frictionless and cancel out friction here, then we're going to find that exactly the x is going to occur at equilibrium, right, as we'd expect. Okay. And then as k gets bigger, the location of x gets smaller and smaller. So in other words, it's getting closer, and that's even with a fixed mu k. And the reason for that is because as you grow k, you're sort of washing out the effect of friction, because you're making the spring so strong that even though there's friction, the spring is still behaving as if there's not friction, because it's dominating the motion. All right, so finally, with that result making sense and catching the mistake in the figure, let's plug in some values real fast. So if we go over here and we plug in our mu k and so on, okay, so our mu k in this problem is 0.3, okay, so 0.3, and then we're just multiplying that by m and by g. Okay, so our m was 1.6 kilograms. G obviously is 9.8, okay. And then we're dividing by our spring constant, which is 45. Okay, so we get a distance of 10.5 centimeters, or 0.105 meters. Okay, so that's telling us that Vmax occurs, if this is 0.28 on the figure up here, Vmax is going to occur somewhere right around here. Okay, so this is location of Vmax. Okay. All right. Thank you.